The recent reemergence of algorithms for permuting models into functionally equivalent regions of the solution space brings us a step closer to understand error surfaces complexities. However, finding the permutation that minimizes some objectives is challenging. In addition, current rebasing techniques are not differentiable, which make it difficult to integrate into a gradient-based optimization and often leads to suboptimal solutions. In this work, we propose a single rebasing network with the ability to obtain the transportation plane that better suits a given cost. Our method is differentiable and therefore easy to adapt to any task within the deep learning domain like model alignment, linear mode connectivity, and incremental learning. There are many transformations that introduce symmetries into the loss landscape. Here, we relied on the well-known permutation transformation. Such a transformation allows us to obtain functionally equivalent models using a transportation plan composed of several permutation matrices Pi. Now, there is an issue with the permute model definition. The binary nature of these permutation matrices forces us to lean into integer optimization techniques to perform the rebasing effectively. This has been proven challenging for others, especially when adapting to new objectives. In this work, we relax the constraints of the optimization task by using soft permutation matrices along with the single operator definition given by Menn and co-authors and using the efficient differentiation proposed by Eisenberger et al. Finally, our single rebasing network is completely differentiable, allowing us to perform rebasing for any given differentiable objective. Here, we propose three new cost functions for simple tasks like model alignment and linear mode connectivity. A more sophisticated loss for incremental learning is also proposed by minimizing the barrier between the current and rebased models but computing the cost over the new knowledge set. All three tasks were approached using only rebasing and can be solved with your favorite gradient descent-based algorithm. For this first experiment, we explored the model's alignment task. Here, we created a control environment where a random permutation is applied to every layer of a model A leading to model B. Then, the goal of the experiment is to apply the rebasing to model A while having B as a reference. The proposed L2 rebasing cost was used in all cases. As can be seen, not only we were able to find the right permutation plan in every configuration, but we significantly improved the rebasing quality compared to the current state of the art. We test our approach with feed-forward neural networks, BGGs of different depth, and ResNets. The optimization converged in all cases in less than 50 iterations. For the second experiment, we target linear mode connectivity. The experiment's goal is to rebase a model A so that it has near constant loss along the linear path that connects it to the model B. This is a highly relevant task since it helps in the understanding of the loss landscape and is the core for several practical applications like incremental learning and ensembling. Once again, our results significantly improve the performance in terms of barrier and area under the curve when compared with naive path and Ainsworth et al. Proposals. We show our method for both regression and classification tasks. Our L2 cost performs similar to weight matching for BGG11 architecture, but outperformed the competitor in deepest scenarios like BGG19. ResNets and bigger datasets like ImageNet subsets were also analyzed with margin to improvement if combined with techniques like repair. On the incremental learning front, our goal is to avoid catastrophic forgetting when adding new knowledge to a previously trained model. In our setup, we look for the permutation matrices that allow us to add a new knowledge without moving too far from the original model. For this end, we use two common benchmarks and architectures within the area. accuracy, and forgetting metrics were used to compare our proposal with the classical approaches from the literature. Our performance surpasses or matches the method used for comparison, which is remarkable since the technique is simply a repurpose of our middle point cost for linear mode connectivity. Even more, the outstanding low forgetting values encourage advancing the incremental learning field, and in future works we plan to investigate the topic further. In conclusion, we propose a new gradient descent-based RIP-based algorithm that can be easily adapted to new objectives. We explore the model's alignment, linear mode connectivity, and incremental learning tasks with the corresponding cost functions proposal. Finally, our implementation targeted simplicity where rebasing netcast a previously defined model, and from there the optimization goes like any regular training cycle in PyTorch. Thanks for watching, and please visit our project website for more details.